Hello everyone. In this lesson we're going to look at drawing Lewis structures. We're going to do an easy example and a little bit more complex example. I might do the second one twice. We're going to start with NH3. Now first we should name that. That is nitrogen trihydride. Right? It's a molecule, it's got covalent bonds, so it follows the prefix naming rule. We're going to start by drawing the electron dot diagrams of the individual atoms. So there's nitrogen, it's got 5 valence electrons, and here's hydrogen, it's got 1. Now, remember, hydrogen only makes 1 bond, it fills its octet, which is really only 2 because it fills that S shell. And NH3, and when we draw this, it's really easy to see, oh, well, this is just going to go ahead and triple bond like that. In fact, I've basically just drawn this thing, right? I've got hydrogen, hydrogen, hydrogen. Everything obeys the octet rule. Remember, hydrogen only gets 2, 2, 4, 6, 8 for nitrogen. I've got nitrogen trihydride. That was really straightforward. But what happens when we get to something like sulfur dioxide? So sulfur dioxide, if I give you the name, you should be able to come up with the chemical formula. That would be SO2. And now I want the Lewis structure for that thing. This is a little bit more complex because sulfur has 6 valence electrons, just like oxygen has 6 valence electrons. And we tend to think that paired electrons don't bond because they're already paired up, right? We've already got 2 electrons in that orbital, and orbitals only hold 2 electrons. But you can look at this and cheat a little bit, and we could say, well, all right, it's clear to see that that unpaired electron can bond and that unpaired electron can bond, but what happens with these unpaired electrons? Well, we can say they bonded right to that pair of electrons, and so what we have now is we have sulfur with a lone pair of electrons that didn't bond, a double bond to oxygen. It has 2 lone pairs, and another double bond to oxygen that also has 2 lone pairs. Now, if we look at this, it's a little bit weird because oxygen, 2, 4, 6, 8 valence electrons, it's obeying the octet rule. Oxygen, 2, 4, 6, 8 valence electrons, it's obeying the octet rule. Sulfur, 2, 4, 6, 8, 10 valence electrons. That's not obeying the octet rule. That's got more electrons than the octet rule accounts for. But remember, sulfur is actually down in the 3rd period on the periodic table, which means it has 1s2, 2s2, 2p6, 3s2, 3p4, and it gives, that's where its 2 open spots come from, right? But it filled those 2 spots by sharing 2 electrons with oxygen, but then it filled 2 more spots by sharing 2 other electrons with oxygen. Where did those 2 spots come from? Well, remember, the 3rd energy level actually has d spots. Now, we know that the 4s's fill first, but the 3d orbital actually is there, and there's open spots for it. So sulfur is actually what we call hypervalent. It can expand its octet down into the d orbitals. So these 2 electrons, that's not a problem. It can bump those into the d orbitals. There's a spot for them. It is obeying the octet rule in that it's got its 3p6, so it does get to look like a noble gas with its s and p orbitals. Now there's another way of doing that, and I kind of want to show it to you. So if we look at sulfur and oxygen, we know we have sulfur, oxygen, oxygen. They each have 6 valence electrons. That gives us a total of 18 electrons to place around these things. Generally speaking, the least electronegative atom will be in the center, and more electronegative atoms will go around the end. So what we do is we start with a skeleton. We put our least electronegative atom in the middle, our central atom, and then we put our other atoms on the ends. We call those terminal atoms, and then we place the rest of our electrons, starting on the terminal atoms, obeying the octet rule, and anything that's left over is going to go on the central atom. So remember, each bond counts as an electron, or a pair of electrons, so that's 2, 4. We had 18 total to start with, 6 plus 6 plus 6, so we've got 14 left to place. So 2, 4, 6, 8, 10, 12, and that is our 8 valence electrons around our terminal atoms, and then we place our last one right there, and we get all of our valence electrons. Now this doesn't look like that. That one's got double bonds, this one has single bonds. Well, now we try to get our octet rule obeyed everywhere by sliding pairs of electrons into bonds. So oxygen can take this pair of electrons and it can share it with sulfur, 2, 4, 6, 8, but this pair is also going to come over and share with sulfur. So now we actually do have the same thing. We have sulfur double bonded to each oxygen atom. Each oxygen has 2 lone pairs of electrons, and sulfur has a lone pair of electrons. Okay. So occasionally you will see in atoms in the 3rd period and beyond that they can expand their octets and actually have more than 8 valence electrons. That's okay. There is a d orbital there that can hold those electrons.